Okay, welcome back to math class. Before we launch straight into this lesson, you may want to pause this video and refresh yourself on what we learned in 8-4. If you remember, in 8-4, we talked about what happens when we have a plus b times a minus b. We called this the product of a sum and a difference. We learned in 8-4 that the product of a sum and a difference equals a squared minus b squared. Now what we're learning today is that we already know that a plus b times a minus b equals a squared minus b squared. So it's also safe to say that a squared minus b squared equals a plus b times a minus b. So essentially we're taking what we learned in 8-4 and we're doing it backwards. We're starting from our endpoint from before and working our way in the other direction. So let's look at that with some examples so that hopefully it makes a little more sense. We're going to look at, what if I had 81 minus c squared? Now what I have to figure out here is this a perfect square? Are both of these a perfect square? Now obviously c squared is c squared, but is 81 a perfect square? Yeah, 81 is 9 squared. So we're going to rewrite them like this, because that's going to tell us what our a and our b are. Once I've got it written like 9 squared and c squared, now all I have to do is take this equals 9 is in our a spot, so I'm going to go 9 plus c times 9 minus c. Pretty easy. I just did the whole thing backwards. If you can figure out that this is a perfect square and that's a perfect square, and I'm subtracting them, then I can just rewrite it just like this. Let's look at another one, a little bit more complex. 9x cubed minus 4x. Okay, now when I'm looking at this, neither of these are perfect squares to start out with because I have x cubed and I have x to the first. And both of those aren't perfect squares, but what I can do when I'm looking at this is I can say I have a greatest common factor that I can go ahead and pull out, and in this case, that's 1x. So I can rewrite this problem as x times 9x squared minus 4, and now 9x squared is a perfect square, and so is 4. So I can take this and I can rewrite it as x times 3x squared, right, minus 2 squared, because that's the square root of 9x squared is going to be 3x, and the square root of 4 is going to be 2. So we know that 4 is the same as 2 squared, and 9x squared is the same as 3x squared. So I'm going to take this, just like before, and I'm going to plug it straight back into this, now that I know what my a is and my b. I'm going to go x times 3x plus 2 times 3x minus 2. Still doing the same thing backwards, but this whole time I've still got to keep track of this x that I pulled out at the beginning. It doesn't go away because I factored it out. It just is the first step of factoring. So now we have x times 3x plus 2 times 3x minus 2. So I know what you guys are thinking, where's the catch? And it does keep getting a little bit more complicated, but as long as you remember your rules, you can keep it straight. So let's try one that's a little bit more complicated. It looks like this. 4a to the fourth minus b to the fourth. Now you'll notice that this is something raised to the fourth, not just raised to the second power. But these are still perfect squares. Because if I take the square root of 4 times a to the fourth, I'm actually going to get 2 times a squared, right? And if I take the square root of b to the fourth, I'm going to get b squared. So these still are perfect squares, they just seem a little bit more complicated. And we now have our a and our b that we can plug in here, so this becomes 2a squared plus b squared times 2a squared minus b squared. And we're done. Still just like the other ones, it just looks a little bit more difficult. One more layer of complication is what happens if what you're given is not just a binomial. What if it's a polynomial with more terms? So let's look at 2m cubed plus m squared minus 50m minus 25. The first thing I'm going to do when I'm looking at this, since it has 4 terms, is I'm going to try to factor it by grouping. And I think that'll work because we have, both of these have m squared in common, and both of these have a negative 25 in common. Okay, so I'm going to factor it by grouping just like we did a few days ago, and do m squared times 2m cubed divided by m squared, which is going to be 2m, plus m squared divided by m squared is going to give us 1. Right, now if I take negative 25 out of both of these, I'm going to end up with minus 25 times negative 50m divided by 25 is going to give us 2m, and negative 25 divided by negative 25 is going to give us 1. Okay, so just like when we factored with grouping every time, what's inside the parentheses in this term matches what's inside the parentheses of this term. So we can go ahead and combine these and get m squared minus 25 times 2m plus 1. Now 2m plus 1 is as simple as we can make it. It's what we called in the last lesson yesterday a prime polynomial. We can't factor it anymore. But if you look at this one, this is a perfect square minus a perfect square. So we can use our differences of squares that we've just learned about today. So I'm going to take m squared minus 25, and I'm going to rewrite that as m squared minus 5 squared, right? Because the square root of 25 is 5. Still keeping this here. It doesn't go away. Now we know when we have a perfect square minus another perfect square, I can rewrite it just like this. So this whole thing is going to become, here's our a, here's our b. So we can rewrite that as m plus 5 times m minus 5. That's what equals this, and then we have to keep this with it. So we're going to say 2m plus 1. So this whole long thing, we have to do in 2 steps. We had to factor by grouping first, and when we tried factoring by grouping, we realized we could also find the difference of squares. So it has 3 binomials that we could factor it out into. I know that's a level of complication, but as long as you use everything that you know and you do it one step at a time, you're going to do a great job at this.